Hello dear students. So now we are going to learn about the small world model, also called the Watt-Stokes or WS model. It is a special type of random graph designed to capture two important properties found in many real-world networks. So short average path length, high clustering coefficient, and this model was proposed by Duncan Watts and Stephen Stokes in 1998. So the real world interactions. Usually a person has a limited and fairly fixed number of connections. For example, in a classroom, each student may regularly interact with a particular group of nearby classmates. In graph terminology, we can represent this situation using a regular graph, where nodes follow an organized connection pattern. So this is the concept of a small world network. A ring regular lattice. A ring regular lattice is a special type of regular network. Imagine all people arranged in a circle. Each person is connected to people close to them on the left and right. For example, if the degree is fixed, every node connects to the same number of previous and the following neighbors. So the network is highly organized and regular. So generating a small world graph. So a regular lattice has two important properties: high clustering coefficient, high average path length. High clustering is good because nearby nodes are strongly connected. But the problem is the path length. To reach a distinct node, we may have to travel through many intermediate nodes. So the next we will use the concept rewiring. So we introduce the concept randomness. The small world model uses a parameter P to control how randomness is introduced. So here it is in beta. So beta is equal to 0, there is no randomness. So the network remains regular lattice. As P increases, more edges are rewired. When the randomness becomes very high, the network approaches a random graph. This is the rewiring concept. So rewiring of links from left to right, there are three graphs. And then connecting small world networks. Sorry, constructing small world networks. So when constructing the network, we have to follow the rules. First, we don't allow self edges. That means a node cannot connect to itself. Second, we don't allow multiple edges. That means two nodes cannot have duplicate connections. These restrictions make the generator network a valid graph. So this is the algorithm for constructing the small world network. So the next one is small world network properties. So the first one is, so the main thing is regular lattice versus random graph. So a regular lattice has high clustering coefficient and high average path length, but random graph has low clustering coefficient and average path length is relatively good or short. So what happens in between? This is the most interesting point. Does a smaller average path length necessarily mean a smaller clustering coefficient, or does a larger average path length mean larger clustering? So to understand this, researchers use numerical simulation by increasing the rewiring probability P from 0 to 1. So the next one is, degree distribution. So degree distribution of the real world small network is the, so this is the regular lattice versus random graph. Then what happens in between? Here the observation is Average path length decreases very quickly, but clustering coefficient decreases slowly. So that when a small percentage of links are rewired, something interesting happens. The average path length becomes much smaller, while the clustering coefficient is still relatively high. For example, 1% of links are rewired, 10% of links are rewired. The intermediate region is called the spot. This is where we get a small world network. So that the clustering coefficient, the change in the clustering coefficient, the, the changes in the clustering coefficient means that when p equal to 0, we have a regular lattice. The clustering coefficient average path lengths are therefore the values of the original lattice. As rewiring starts, some triangles are broken. The probability that a connected triple remains connected depends on whether its edges have been wired. So this is the 1% of links wired and 10% of links unwired. Then modeling with the small well network. So suppose we know two properties of a real well network, average degree and clustering coefficient. We use the average degree to construct the underlying lattice and determine the rewiring probability using the appropriate equation. So for example, suppose a real world social network has 1000 nodes, average degree equal to 10, high clustering coefficient. We construct a regular lattice with the appropriate degree and then choose a suitable rewiring probability. So, so that the okay. So now real world network and the simulated graphs. Finally, we compare the real world network with the simulated small world graph. The purpose is not necessarily to reproduce every single connection. Instead, we simulated network to reproduce important structural properties such as similar average degree, similar clustering, and short average path length. This is why the Stochastic model is useful for understanding the real-world network. Then quick summary of this lecture is, so we can start with the regular lattice and rewire a small number of edges and then get short paths while retaining high clustering. The key concept is called the sweet spot. A regular lattice has high clustering but long paths. A random graph has short paths but low clustering. The small world model gives us an intermediate network with high clustering plus short average path length. That combination is what makes a network a small world network. Thank you, students.